Introduction and Basic Concepts. Welcome to Fluid Mechanics 1. In this first chapter, we'll go through the introduction and some basic concepts. Why start here? Because it's impossible to understand flow problems or pressure systems without getting these fundamentals right. Fluid mechanics is all around us, whether you're watching waves at the beach, driving your car, or even drinking coffee. But before we jump into complicated equations or big systems, we need to answer simple questions. What exactly is a fluid? How is it different from a solid? What basic properties should you always think about when dealing with fluids? This chapter is like laying the foundation before building a house. If you skip it, the whole structure won't make sense. So let's keep it simple and clear, step by step, starting from the very beginning.
1. Introduction. Let's break down what we mean by fluid mechanics. Think of mechanics like a big family tree. At the top, we have two big branches: statics, which looks at things that don't move, and dynamics, which focuses on things that do move. Fluid mechanics sits under dynamics, but with a twist. It also studies fluids when they're not moving, called fluid statics, and when they are moving, called fluid dynamics. Then we get more specific. Hydrodynamics is all about liquids that don't compress, like water flowing through rivers. Gas dynamics deals with gases, but especially when they compress, like air moving fast in rockets. Aerodynamics, that's about how air flows around objects, like planes or cars. Hydraulics, that's about liquids moving in pipes or channels, like water in plumbing or oil in hydraulic presses. So every term you see here has a specific job, and knowing the difference early on will make everything clearer later on.
2. What is a fluid? What actually makes something a fluid? It's simple. A fluid is any substance that keeps deforming when you push on it. Imagine pushing on honey or water. It keeps moving as long as you apply force. That's what we call continuous deformation under shear stress. Solids are the opposite. When you push on a solid, like a brick, it resists, maybe bends a little, but it holds its shape. Fluids never hold their shape. And here's a key point. Fluids aren't just liquids. Gases count too. The difference is that liquids hold their volume, but change shape, while gases not only change shape, but also expand to fill any space they're in. So every time you drink water or watch steam rise, you're watching fluids behave exactly how this definition predicts. 3. Application areas of fluid mechanics. Fluid mechanics isn't just theory, it's everywhere in real life. Let's think about where it shows up. Every time you open a faucet or design a piping network, that's fluid mechanics in action. Hydraulics? That's all about controlling fluids to do work, like in heavy machinery or car brakes. Aerodynamics affects how cars cut through air and how planes stay in the sky. In medicine, it helps us understand blood flow or build artificial hearts. And if you've ever wondered how we predict weather or study ocean currents, that's fluid mechanics too. These examples show why it's a core part of engineering. It solves problems that matter across industries. 4. A brief history of fluid mechanics. Let's see how fluid mechanics has evolved over time. It didn't just appear overnight. It grew through brilliant ideas from famous thinkers. It began with Archimedes, who gave us the concept of buoyancy. Think about why things float. Then Newton explained how fluids respond to force and introduced viscosity, explaining why honey flows slower than water. Bernoulli showed how speed and pressure are linked, which is why planes can fly. Later, Navier and Stokes gave us the fundamental equations to describe fluid motion, and Prandtl explained how thin layers of fluids behave near surfaces, super useful for understanding drag. Finally, modern engineers use powerful computers to simulate all this in detail using CFD, computational fluid dynamics. These key moments show how fluid mechanics has advanced from simple experiments to high-tech simulations. 5. The no-slip condition. Let's talk about something that sounds simple but is hugely important: the no-slip condition. This rule says that whenever a fluid touches a solid surface, its speed drops to zero right at the contact point. It doesn't slip or slide past the surface. This tiny detail explains why fluids form boundary layers near walls. And why does this matter? Because it's the starting point for understanding drag, turbulence, and how heat moves between surfaces and fluids. Whether it's designing faster cars, efficient cooling systems, or smoother pipelines, it all starts by knowing that the fluid sticks to the wall. 6.1. Classification of fluid flows. Classifying fluid flows helps you pick the right tools for analysis. First, there's viscous versus inviscid flows. Viscous flows happen in real life, think honey or oil, where friction slows things down. Inviscid flows are a shortcut for simpler calculations where we pretend there's no viscosity, handy when friction doesn't change the big picture. Next, we split flows into internal and external. Internal flows happen inside pipes and ducts, like water supply systems. External flows happen around objects, like air moving over airplane wings or cars. Knowing these differences keeps you focused. You choose your equations based on what matters, friction or not, inside or outside. 6.2. Classification of fluid flows. When classifying flows, two more distinctions really matter. First is compressible versus incompressible flow. Liquids almost never compress, so they're treated as incompressible. Gases can compress, but when their speed is low, less than 30% of the speed of sound, we can often simplify things and call them incompressible too. This helps avoid complex equations when we don't need them. Next, we split flow into laminar and turbulent. Laminar flows are smooth and predictable, like honey pouring slowly. Turbulent flows are the opposite, wild, swirling, and unpredictable, like rapids in a river. Knowing which type you're dealing with changes everything about how you calculate and design systems. 6.3. Classification of fluid flows. When classifying fluid flow, you also need to ask what's driving the flow, is it changing over time, and how many dimensions matter. First, natural versus forced flow. Natural flow happens on its own because of buoyancy, like hot air rising. Forced flow needs help, like pumps pushing water through pipes. Next, steady versus unsteady flow. Steady means the flow stays constant. Unsteady means it changes, and sometimes it's even periodic, like waves going up and down. Finally, you have 1, 2, or 3-dimensional flows. That just means, do we care about velocity changing in one direction, 2 directions, or all 3? This classification keeps your analysis focused, so you only model what actually matters. 7. System and control volume. Before you can solve any fluid problem, you have to know what system you're dealing with. A closed system is simple. You track a fixed mass, no mass enters or leaves, like a sealed gas container. An open system, or control volume, is different. Here, mass flows in and out, like water through a turbine or air through a jet engine. And the boundary? That's just the line you draw around your system, real or imaginary, to separate it from the surroundings. Getting these basics right keeps your analysis clean and helps you avoid confusion later, because all your equations depend on how you define your system. 8. Importance of dimensions and units. Let's talk about dimensions and units, something simple but crucial. Every equation you use depends on 4 basic building blocks: mass, length, time, and temperature. These are called primary dimensions. Then come the units. Most of the world uses SI units like kilograms and meters, while the US still uses English units like pounds and feet. To keep equations valid, we follow dimensional homogeneity, meaning every term in an equation must match dimensionally. And when you need to switch units, unity conversion ratios make life easier by letting you multiply by 1 without changing the actual value. Getting dimensions and units right saves you from big calculation mistakes later on. 9. Modeling in engineering. Engineering relies on 3 main ways to solve problems. First, experimental methods. They give you real-world results, but take time and cost a lot.
You need labs, equipment, and setup. Second, analytical methods. These use mathematical formulas. They're faster, but usually based on simplifications, so they give rough estimates. Finally, computational methods, especially CFD or computational fluid dynamics, let you simulate complex problems on a computer. CFD helps when experiments are too expensive and analytical formulas are too simple. Knowing when to use each method keeps your designs efficient and your solutions practical. 10. Problem-solving technique. Solving engineering problems needs a methodical approach, not random guessing. Start by writing a clear problem statement. Know exactly what you're solving. Next, draw a simple schematic. Visualize it before jumping to math. Then, make smart assumptions. Keep it realistic but manageable. Use physical laws like conservation of mass, energy, or momentum. They're your foundation. Look up the right properties for materials or fluids you're using. Then, do the calculations using proper equations and numerical methods. Finally, always verify your results. Ask yourself, do they make sense? A clear, step-by-step process helps avoid mistakes and saves you from unnecessary confusion later. 11. Engineering software packages. Let's talk about the tools you'll actually use. Engineers don't just calculate by hand, we use software to work faster and solve bigger problems. EES, or Engineering Equation Solver, is great for quickly solving algebraic equations, especially in thermodynamics and fluid mechanics. It's simple but powerful for textbook-style problems. For complex fluid flows, we use CFD, Computational Fluid Dynamics software. CFD handles complicated situations like turbulent flows around cars or aircraft by simulating everything on a computer. Learning these tools means you'll spend less time struggling with math and more time understanding and solving real engineering problems. 12. Accuracy, precision, and significant digits. Good results in engineering aren't just about solving equations, they're about measuring things properly. Accuracy tells you how close your measurement is to the real answer. Precision tells you how repeatable your measurements are. You want both. Only report significant digits. Don't write down meaningless extra numbers. They just create false confidence. Watch out for errors. Systematic errors happen because something's wrong with your setup, like a miscalibrated instrument. Random errors happen from unpredictable variations, like tiny fluctuations in readings. Knowing the difference between accuracy, precision, and error types keeps your answers realistic and trustworthy. 13. Summary. Let's wrap this up by making it simple. Fluid mechanics is about understanding how fluids move and interact. It's useful in engineering, but also in medicine, like blood flow, and in environmental science, like predicting weather. We classify flows by how viscous they are, whether they compress, if they're smooth or turbulent, and how many directions the velocity changes. To solve problems, we use mathematical models, experiments, and computer simulations. Tools like EES make math easier, and CFD handles complex flows. Mastering these basics helps you tackle real-world problems with confidence and efficiency.